Now in this video, we will be talking about the transistor again, but here we will be discussing the main important application of this transistor, that it can be used as an amplifier, and we will discuss this thing in terms of common emitter mode of a transistor. So what we are going to discuss here is the amplification that we can have by virtue of a transistor. Now, this transistor is also called an amplifier because it can enhance, it can increase the amplitude of the input signal. So a device which increases the amplitude of the input signal is called as amplifier. Now, the input is always weak, and the output that we are going to obtain from this is, so this is my amplifier. Now this is the transistor in common emitter mode, and we have the input, right? So the input signal is weak, and the output, in case of common emitter configuration, we have the output out of phase. So it will be amplified, but at the same time, its amplitude will be increased. So we have the weak signal as input, and this weak signal is fed to the amplifier, which in turn amplifies the signal, and we get the output signal of large amplitude. And in case of common emitter configuration, we are not only able to amplify the signal, we can have the inversion of the input signal. The output signal will be out of phase with respect to the input signal. Now, we better understand that when we have a common emitter configuration, as we talked about the transistor, it has input circuit and it has output circuit. Now in the transistor, the emitter base junction that qualifies for input circuit, which is being forward biased, it has low resistance. So the input circuit, that in this case, between emitter and base, it has low resistance. Okay, so low resistance, right? And then we have the collector base junction, the output circuit, which is being reverse biased. In this case, in out circuit, we have base and collector, and here it has high resistance, right? High resistance. So almost all input, emitter current flows in the collector of this transistor. So we have to bear in mind that thing. The right thing at this point would be that I would like to draw the circuit in common emitter configuration and discuss the results. But if I go back to what I said, is the input has low resistance and the output circuit has high resistance. Because of this, in a transistor, there we have a transfer, the transfer from the input signal current from low resistance circuit to the high resistance circuit. So this fact is basically responsible for amplifying the capability of the transistor. So this mismatching of the resistance between input circuit and output circuit. And in this common emitter amplifier, input signal is to be amplified. It is to be applied between base and emitter circuit, and output signal will be taken across the load resistance. So I would like to redraw this configuration so that we understand the amplification by virtue of this transistor in common emitter mode. So we have a transistor. Okay, so as usual, I would like to choose the NPN transistor. So the arrow should be outwards, and this emitter will be grounded, and then we have the base here, and here I would like to give the input signal, which is weak in magnitude, and I would like to bias the input circuit. So this should be positive, negative, and positive, and this should be like this. Okay, so this is my input. So let me assume that this resistance is RB, and this is my emitter, this is my base, and this is my collector. All right, so things are clear up to now. So this is an NPN transistor, and I would like to write here, this is an NPN transistor. NPN transistor. So now let's go with the output circuit here. So we will have the collector current, and we will have a load resistance, and we will bias it so that this should be positive, and we'll connect these two, and we'll ground this all, and I'll name this as VCC. So I will name this as VBB, as I did in the previous video, and here I'm going to give the input signal. So the input will be here. So let us assume that I have an input voltage with respect to time as this signal, and then finally we will have the output, and that output will be obtained across this load resistance, and that will be V out. Right, that should be the case. Now this is the load resistance RL, and here we have IC. Okay, that's clear. And then we will have we'll have to analyze this circuit now for input and output. Now you can see here that the input signal to be amplified, it is applied across the input circuit. That means it is applied across base emitter circuit. Now the input circuit is to be forward biased, okay, using a battery of EMF equal to VBB, volts. Right, so this is in volts. Now the output, the amplified output signal is taken across this load resistance. Right, in the output circuit, the collector and emitter, the collector and emitter, it has to be reverse biased, right? And the EMF of the battery that we use here is equal to VCC volts. Now, if we apply the Kirchhoff's law, Kirchhoff's junction law, in that case, between the emitter, here we have the emitter and base IB. This must be my IB, okay? So this is IE and this is IB, and collector current. We can easily write down for a junction, this IE is equal to IB plus IC. No issues. Now the point is, when IC, when collector current flows through the load resistance RL, the output or the collector voltage, this V out that we have here, it must be equal to VCC minus ICRL. Very simple, from Kirchhoff's law on applying KVL in the output circuit. So when we use that KVL, so we can think of writing the equation for output as V out is equal to VCC minus ICRC. Okay, so these are the two realities of this circuit. And now what's going to happen, let's try to understand that how does this transistor amplify the signal that's input to its base, and at the same time try to understand how does it invert the signal that we use as input in this case. Now during this positive half cycle of the input signal, the forward biasing of this emitter base junction increases. Certainly, now due to increase in forward bias, this emitter current will certainly increase, and hence according to this equation, say this is equation 1 and this is equation 2, then according to this equation the collector current also increases. That should increase, right? Therefore, the voltage drop from this equation, the voltage drop across RL increases. So this value increases. Now, if this value increases, then according to this equation, you can see here the collector voltage or the output voltage of the output voltage decreases. So here we have increased voltage, but here we have decreased output. Very simple way of understanding it. Now, since the collector is connected to the positive terminal of the battery here, you can see it's connected to the positive terminal of the battery. So decrease in VO. So this decrease in VO means that the collector voltage becomes less positive. That should be clear, that the collector voltage that we will have is less positive. Now, to talk the same thing in other words, the amplified signal that we have the amplified negative signal is obtained across this output, right? Now, similarly, let's do the same experiment in terms of the negative cycle. Now, during the negative half of this cycle of the input signal, the forward biasing of this emitter and base junction, it's going to decrease. That's clear. Now, as a result of this, the emitter current and hence the collector current will decrease. So this collector current is going to decrease. Therefore, the voltage drop across RL. So what's going to happen here is that the voltage drop that we will have across this RL, in terms of this parameter ICRC, it will also decrease, right? Now, if this decreases, hence according to this equation that I'm saying, this equation, the output that we obtain here, the output, or you can call the collector voltage increases. Since the collector is connected to what? It is connected to the positive terminal of the battery VCC here. So increase in the output means that the collector voltage becomes more positive. Thus, what's going to happen is we have the amplified positive signal is obtained across the resistor RL. So since we are in common emitter configuration, because we can see here that the emitter of this transistor is common between the input circuit and the output circuit. So this is my input circuit and this is my output circuit, right? This is my output circuit, this whole thing. So so what we have obtained from this discussion is that the output voltage decreases with increase in input signal and increases with the decrease in the input signal. So this increases, the output is decreased. In addition, there is amplification, right? And here we decrease, but the output increases. So this is the voltage, this is the time. So you can see here that the output signal that we obtain here is out of phase with respect to the input signal. And in addition of that, the magnitude of the signal has increased. So this way we can say that in common emitter configuration of a transistor, and the transistor we have chosen here as NPN transistor, the input signal, the polarity of the input signal changes. There is a phase difference between the output signal and the input signal. At the same time, the amplitude of the signal increases.